In order to do practical quantum computation, there are many requirements and many things that need to be fulfilled. For example, we will need many qubits. Those qubits need to be able to interact with each other. But it's also very important that the performance of those qubits is very high. Now, the performance of the qubits may mean several things. For example, if we have a large array of qubits, we may want that qubits on the outsides of the array interact with each other. And we want that interaction can be with a very high fidelity, or with a very high performance. We also would like to see that if we do an operation somewhere, that the quantum state of qubit somewhere else can survive during the quantum algorithm. So we want to have a very long quantum coherence. That quantum coherence will also determine actually how good we can do an operation on an individual qubit. And so a particular aspect is also how good is the performance of the operations one can do on a qubit, the single qubit gates, as well as how good can one couple different qubits to qubit gate fidelities. Here we'll focus on the first part, the quantum coherence of the qubits and the fidelity of operating quantum gates on a single qubit. So first of all, let's go back to the material science and the developments over the years throughout, and look at the aspect of the quantum coherence. So first thing one may wonder is, okay, if I prepare a spin-down state or a spin-up state, how long would it remain in that state? Turns out that for both states, and in particular the spin-down state, that state will remain for a very, very long time. But also in the excited state, if it's a spin-up state, it will take a very long time before it relaxes down to the ground state. And the reason for that is that in semiconductor spin qubits, there's not a real source that can provide a strong relaxation. There's one caveat. Once we start to couple different qubits, then there may be a difference, and this relaxation may actually be faster. So if we're doing readout via pilot spin gate, or maybe do 2 qubit gates, then there may be instances that we need to consider also the relaxation rate. But for qubit in isolation, the relaxation can be very long. So the key question then is, okay, if I prepare a superposition state, what will be its quantum coherence? So in gallium arsenide, just by preparing a coherent state and let it freely processing over time, we find that on the order of 10 nanoseconds is the dephasing time. This time can be improved by applying pulses throughout. Actually, it turns out that most of the times driving a qubit is better than letting your qubit freely processing. For example, by applying a simple pi pulse halfway the experiment, we can correct for low frequency noise. This is called a Hahn echo experiment, and which can extend already to microsecond timescales the coherence in gallium arsenide. And using more sophisticated techniques, as well as several of those pi pulses, this can also already increase the coherence to several hundreds of microseconds. Now, another thing we can do is by changing material. In gallium arsenide, hyperfine interaction causes nuclear spin noise, and that causes the main source of the decoherence. By moving to silicon, in particular silicon-28, this coherence can be extended quite a bit. In particular, in silicon, we obtain coherence time on the order of a microsecond and up to 120 microseconds in silicon-28, which can then be further improved again by applying those echo pulses. Now, a natural question is then to ask, what will happen in germanium? Germanium, like silicon, is a group 4 material, so naturally it already has a large abundance of nuclear spin-free isotopes, and it can furthermore be enriched to purified germanium. However, in germanium there's also spin-orbit interactions, and these spin-orbit interactions cause that the G factor, or more specifically the G tensor, is not very well defined in germanium, meaning that if we displace a qubit a little bit, the G tensor changes, and this G tensor can then lead to changes in the resonance frequency and lead to decoherence. So our question then is, okay, we may be able to use these variations in the G tensor to drive a qubit, but it may also lead to decoherence. So what will happen with our performance in germanium? So first we'll focus on the coherence itself. So here we see that the coherence is typically on the order of a few hundred nanoseconds, which becomes larger if we change the magnetic field. This is expected if we have electrical noise, because the electrical noise can only couple in by some mediator, in this case the fluctuations of the G-tensor, that are amplified by the magnetic field to change the resonance frequency. So the smaller we make the magnetic field, the smaller the resonance frequency, and therefore also the smaller the fluctuations of the resonance frequency. By going below 100 millitesla or so, we can even find that we coherence times of actually beyond a millisecond, up to several milliseconds, by operating at tens of millitesla. In particular, this is still in natural germanium. So it may be that by operating at very small magnetic fields, coherence is even longer by making the qubit very insensitive to electrical noise and only hyperfine noise, which may be avoided by isotopic enrichment. Now, at the same time, it seems like, okay, then we should just make the magnetic field as small as possible. We also want to do qubit operations. There are several modes of doing that. In particular, for single spin qubits, the common mode is to use EDSR. So we apply electric fields to change the location or the energy space of the qubit and thereby the G-tensor. And this enables to drive qubit rotations. But the speed of those rotations are also determined by the magnetic field in an opposite manner as the coherence is doing. So typically, if we drive EDSR, we want to drive at a slightly higher field. And so we find out that for EDSR-driven qubits, the gain in coherence is kind of lost in the performance of the qubits. Of course, there may still be arguments from a larger perspective to operate either at a lower and higher magnetic field. For example, a higher magnetic field may allow for larger variations between qubits and therefore better 2-qubit gates. On the other hand, a lower magnetic field may allow for longer coherence and therefore, for example, the readout can be slower, for example, if one wants to do mid-circuit measurements. So these are the sort of things to consider, but overall finding a coherence time on the order of 100 nanoseconds to a few microseconds for natural germanium. And this is rather long if we compare that in general the single and 2-qubit gates are in the order of 10 to the 100 nanoseconds depending on the exact sequence we're performing. Okay, now we're saying here that this 1/over dependence suggests that electrical noise is a main factor in determining the coherence. But we're also using natural germanium, so that means that there is some hyperfine interaction. So a question then to us is, okay, can we already observe it? Is there some impact? And a very nice way to probe this is by making use of the transversal interaction. In particular, the nuclear spins are anisotropic, and that has several consequences. First of all, the interaction is expected to vanish because of the py-type nature of whole wave functions. But that actually turns out in reality to not be the entire story, because there may be higher order terms through the spin-orbit coupling leading to dipole-dipole interactions. And this gives a rather similar interaction as one would also expect for electrons in silicon. Nonetheless, this interaction has a rather Ising form type of interaction, thus meaning that the directional dependence of the noise is very directional dependent. And this means that if we apply the magnetic field along a certain axis, then the noise is maybe along another axis. I mean, this is something we can exploit. So an experiment we performed is by applying in-plane magnetic fields, doing CPMG sequence to become very sensitive to certain qubit frequencies, in particular set to become sensitive to the Larmor precession of the nuclear spin. And from there we see directly the transversal interaction between the nuclear spin and a germanium Hall spin qubit. And then by probing this as a function of magnetic field, we see a very strong correlation, indeed showing that we can observe the interaction of a Hall spin qubit with a nuclear spin. Now, to analyze this further, we've performed some free radical modeling, and from there we can then deduce that, okay, if we just consider Zeeman noise, we cannot recover this kind of peaks in the decoherence due to the interaction. Hyperfine noise inclusion already allows to capture more. Then even by including the nuclear quadrupole moment, we can nicely capture the experimental data. And so what we obtain from this is that the coherence time, or the dephasing time, for germanium spin qubits is on the order of 6 microseconds if one only considers the interaction with nuclear spin noise in natural germanium. Seeing that already the experimental T2 star is on the order of microseconds, and this is at a higher magnetic field, at smaller magnetic field it's even longer, is already comparable to these timescales. It really means that our field is now close to a time that it becomes crucial to start to operate in isotopic enriched germanium to further increase the coherence. So that was the part on the coherence. We also want to focus on the quality of the operations. A sequence that we often use to probe the quality of the single qubit gates is called randomized benchmarking. In randomized benchmarking, one performs a series of Clifford gates to bring the qubit state to different states on the Clifford positions. And by taking a random series, in one hand it may mimic a true quantum algorithm, on the other hand it also randomizes the noise. And so by this randomization of the noise, then one can extract the fidelity by looking at the decay of the signal. So for a quantum computer, there are predictions that a minimum fidelity is on the order of 99%. What we're observing in germanium already is that this fidelity at the best times for the best qubits can be even above 99.99% fidelity. This is the highest fidelity thus far for semiconductor qubits, and it's really encouraging to see that we can already do this in natural germanium with lots of knobs and proofs to further increase this fidelity by focusing on the material, on the way of operation, by using more sophisticated pulses in the fabrication, and so forth. So this is very encouraging news for the field. Of course, this is only the single qubit gate, and to put it into context, what we want to do is to operate many qubits at the same time. So a key question is, of course, if we do simultaneous operations of many qubits, we will still get the same fidelity. Also, it will be very important to get high fidelity 2-qubit gates, and also to be able to do that simultaneously. Then finally, we want to be able to also connect that over longer distances. So there's still, of course, many things that we need to overcome to put this in a practical context.